Welcome back. Let's continue our topic on chapter 3. Today's lecture is over a specific theorem. It's called the mean value theorem. Here is the theorem, and we will do example to see what it means. Given a function f, and with the fact that f is continuous on an interval a to b, so let's assume we have a function, it's continuous over a closed interval a and b. And the endpoints belong to that interval, so it's a closed interval. And let's assume f is differentiable on the open interval, because endpoints normally you cannot discuss the derivative on one side, so we assume differentiability over interval. Then there's a specific constant c. At least there should be at least a number c, but we'll mention that where is this c. That satisfies the following property, that the derivative at that location c equals f of b minus f of a divided by b minus a. Okay, first let's see what does this mean. The theorem is just has some good consequences. I want to see first what this theorem means. Okay, so let's say you're given interval a to b. And a and b do not need to be positive, but normally it's easier to assume this. And let's say f of a somewhere here. This is f of a, corresponding y value. F of b somewhere here. F of b. Okay. And we assume that f is a continuous function. So it means from point A to point B, you have to connect them through a continuous function. And you cannot create breakpoints, because if you do this, then the function is not differentiable at that point. So we assume there is a smooth function that somehow reaches to that point, maybe something like that. From point A to point B. Okay, what is from the corresponding point A, which is the y value f of a, and to point B, y value f of b. So what this fraction represents in the theorem, f of b minus f of a divided by b minus a, is that if you connect the point A and B together, you connect these two, and I ask you what is the slope of this line. How do you calculate the slope? Is you find the two coordinates and you say the difference in the x1, y1, and x2, y2, y1. You say the difference between the y's divided by the difference in the x's. Right? So you say y2 minus y1 divided by x2 minus x1. This would be the slope of that line. What is the slope of that line? Since you have the point A and B and their corresponding y value, would be y2, which is f of b, minus f of a, y1, divided by b minus a. So what this fraction represents is basically the slope of this line that connects the two endpoints, right? This line is called the secant line, the line that connects the two endpoints. And what it says somewhere along the curve, change this color. It says somewhere along this curve, there's a point where the derivative equals to that slope. What does the derivative represent? The derivative represents slope of tangent line. Tangent line at whatever value given, at c in this case. So it says there is a point c where the slope of tangent line at that point exactly equals to m. And if you look at the curve, that means find out where the point c is. Here is the point c. The slope of this dotted line and the slope of this secant line, they're equal because the two lines are parallel. If you remember, two parallel lines have the same slope. Therefore, there is a point c where the slope of the tangent line, f prime, is exactly m. Yeah, you may say, what is the use of this? This is used if you assume, for example, if you assume that slopes if the endpoints are equal to each other. Say if you have a point A, point B, and the endpoints are equal, that means there is a point here where the slope of the tangent line is 0, which kind of it becomes a local maximum or absolute maximum, or it could be the other way. It will give you an absolute minimum because the two slopes are going to be 0. It would be 0 because the difference in the y's are 0. Therefore, there is such a point where the f prime at the point C equals to 0. Okay. At this point, we want to find out, okay, can we figure out C for different examples? So let's try to look at these examples. I think I wrote 1 or 2 examples, yeah. Okay, so let's look at this question. Given the function f over the interval 0 to 2, we want to find C that satisfies the mean value theorem. Satisfies the mean value theorem. So here, mean value theorem. Okay. So mean value theorem says find out, this is A, that is B, the two endpoints of the interval. So find out the slope, which is f of B minus f of A divided by B minus A. And that slope must be equal to f prime at some specific point C. We're looking for that specific value of C. So the question is, what is C? That's what we're looking for. So find f of B minus f of A. So here, slope is f of 2 minus f of 0 divided by 2 minus 0. F of 2 would be replace 2 into the function. 2 cubed minus 2 is 6. Minus f of 0 is 0 divided by 2 minus 0. So the derivative would be simply, the slope must be 3. That means the derivative at some point C must be equal to 3. We want to figure out what is that C. To find out the derivative first, what is the f prime function? 3x squared minus 1. So we need to figure out f prime at some point equals to 3. So it means 3x squared minus 1 equals to 3. We want to find out where the derivative equals to 3, where these two are equal to each other. Actually, this should be replacing c into the function, but yeah, this should be right, 3c squared minus 1. But I don't want you to get confused, so let's look at it this way. That means we're looking for that x value, that the derivative at that point equals to 3. Add 1 divided by 3, so you'll get x squared equals 4/3. And what is x? X becomes plus or minus square root of 4 over 3, which you can simplify it to 2 over root 3. Okay. You might ask yourself and say, okay, I have two solutions, which one do I accept? You look at the interval. Sometimes you have multiple answers, but in this case, you look at the specific interval and say, okay, negative cannot be in that interval. So our solution, 2 divided by square root of 3. That is the constant C. C equals 2 divided by root 3. That means the derivative at that point is exactly the same as the slope of the secant line connecting the two endpoints. Okay. Here, one more of consequences of this mean value theorem. This is kind of used for approximation. Let me shift this up a bit. Okay. Let's say, suppose f of 0 is given negative 3. So I want you to think about this as given a function at the point 0, y value is given negative 3. So let's say this is negative 3. This is a point. And they say the derivative at every point is given less than 5. How large the f of 2 can be. So this is at 0. We want to find out at 2. What is the y value, that maximum y value that could be? Could be at 200, for example. This is the question. Can y value be 200 or 300 or something like that? So we want to find out the maximum possible y value for 2. Okay, some result that we have from the mean value is says f of the endpoint b minus f of a divided by b minus a is equals to the derivative at some point c. But you have a restriction on the derivative here. The derivative is always given to be less than 5. That means this is always less than or equal to 5, which means since equals to that, this is always less than or equal to 5. So what do I know? The point B is 2. You have 0 for A, B is 2. So you can replace that and say f of 2 minus f of 0 divided by 2 minus 0 must be less than or equal to 5. What is f of 0? F of 0 is given, -3. So I can replace f of 0 with -3. So I have f of 2. Therefore, f of 2 minus -3 divided by 2 minus 0, which is simply 2, is less than 5. To solve this inequality, multiply both sides by 2. You get f of 2 minus -3 becomes +3, is less than 2 times 5, 10. Subtract the 3, f of 2 is less than or equal to 7. That means the maximum y value for 2 must be 7. It doesn't mean that it's going to be exactly 7. It could be 6, 5, or whatever. But the maximum y value that possible satisfy the fact that the derivative always is less than 5 is going to be 7. So somehow the curve, actually it doesn't look like that. You'd have a constant slope of 5 to be possible to get to this point. Okay, so the slope 5, it should be straight line. So the tangent line would have a slope 5 at most. Okay, these are the two kind of examples for this section. It's an easy topic to understand. Just make sure that you draw a picture to see what is this basic idea of mean values here. Okay, I'm going to stop at this point. Next time we'll continue talk about how the derivative affects the graph, and that would be a very important topic.